All right, let's begin. So how was that? Fair. Okay. One of these. This guy was actually on it, right?
Yeah, the example was.
I made it a definite, but if you had done this over the weekend, you would have known like most of that problem. Anyway, so yeah, there's a bonus section, as you would have noticed at the end of the quiz, and that's about stuff that I haven't yet covered, or maybe anything that I wanted to slip in the quiz, but I just didn't feel like there was enough time. So that counts as extra. So this quiz was out of 10 points. So let's say you do all 10 and you get them right, and then you do a few of the bonus problems and you get, like, say 2 right, so you get 13 out of 10. What I do is I mark that quiz as a 10, and those 3 extra points I add it to another quiz later on. So you do great on this quiz, but you mess up on this quiz, you might get a little saving from the bonus points here. So that's it. In addition to me dropping 2 quizzes, so you have a lot of wiggle room here. If you're off for one day, it shouldn't matter too much in this class. It's just try to be consistent. So we are going to continue with these examples that we had to do from last class before we move on to the next topic. Because, you know, as much practice as we can get, we'll get it. So next word, okay, what do you think for this one? Substitution, what would you substitute?
I think you.
So this would become 1/3 the integral of e to the u to u. So again, substitution, the point is to make the integration simpler. E to the x cubed is a very complicated thing. E to the x is very simple. So the fact that the power is a cube makes that complicated. I'm going to want to actually get rid of the cube and the power. So I do substitution for that. And you'll notice here, once I do that substitution, I don't actually need to do anything else. Like, I don't need to by parts. That's just a straight up substitution problem. And so that would be 1/3 e to the x cubed. And of course, we know how to differentiate to check this. The derivative of e to the u is what? U prime e to the u. So it's just going to be the derivative of the power, which is 3x squared. You multiply that, the 3's would cancel, you just get x squared times the original function, so you can get that back pretty easily. F. Tabular?
Yeah.
With what?
X cubed as the differentiated one, and
Okay.
x squared is
So you have 3x squared, you would have 6x, you would have 6, you would have 0. Okay, what's the integral of sine of x squared?
-half cosine squared.
-1/2 cosine x squared. Is that true? If you were to differentiate this, what would you get? If you were to differentiate this, what would you get? You get? There's this chain rule, so there's an inner function and outer function. To differentiate the outer function, it's going to be a minus sine of x squared, right? Times the derivative of the inside, which is 2x, times the -1/2 out here, right? So it will just give you what? It will give you x sine of x squared. So no, that is not the integral. What is the integral of sine of x squared? Yeah? Yeah?
Negative cosine x squared over 2x.
Where are you getting that from? What are you guys thinking about when you think about it? You see this problem, I want to integrate sine of x squared. What goes through your minds? Yeah?
Substitution. That
So if you had the integral of sine of x squared as a problem, substitution?
No, I mean the x cubed sine of x squared.
Yeah, but let's finish this question because I want to make sure that we don't, what's the misunderstanding that's happening here. You see you have to integrate sine of x squared. What goes through your head? Yeah.
Isn't there an identity, like to change sine of x squared?
What's the identity?
1 minus cosine 2x over 2.
No, that's not the identity.
Isn't x squared minus?
Also, sine of x squared and sine squared x, you guys do realize that those are different, right?
Yeah.
Okay, those are two different things. The angle is squared here, whereas for this one, the entire trig function is squared, which are very different situations. The identity you're talking about applies to this one, not that one. Yeah.
I forgot to say that this is a chain rule because it's a function within a function, so...
Chain rule is a derivative rule. We're asking about the integral of sine of x squared. Yeah.
Let u equal to x squared.
Okay, so here's the answer. The integral of sine of x squared is impossible. It's another one of those impossible things. It's one of those things that you should know that you can't actually do. Right? Same way that you can't integrate e to the x squared, you can't actually integrate sine of x squared. Like there's no function you can come up with. Now a lot of you are trying to apply, you're trying to reverse the chain rule in a way that it can't be reversed. So you're thinking, okay, I just take the derivative of the x squared and divide by it. That's not how the chain rule works. That's not how substitution works. If your derivative is not a constant, it does not work. Right? So, in short, jumping right into tabular method is not going to work for this guy. It's not going to, and I just realized that we don't have an eraser.
Aren't you always prepared?
Huh?
Aren't you always prepared?
I should be. But last time I left it here. So let's do another, let's take another crack at this and then I'll go steal an eraser from Tim. So knowing that I cannot actually integrate sine of x squared, other ideas. Yeah.
I rewrote that expression to x squared sine x dx, so when separate,
Okay.
I use substitution
On.
x squared and du equals 2.
Right, so I don't want to use a u substitution because this is kind of going to lead into an integration by parts, and the u from your substitution, I don't want to mix it up with the u from integration by parts. So I would do another substitution, t equals x squared. Now why would I do that? Because I have a rule. I know how to integrate. I know how to integrate that, where there's just a variable with no power on it. This would be something that I would have memorized, that Jhevon's going to quiz me on in problem 1. If I have this, that's not something that's a rule that Jhevon's going to quiz me on. This is the thing, and because you've all done so well in memorizing all these rules, you know it does not apply to that guy. Because here, the angle is squared. The rule you have memorized, the angle is not squared. So you can't just decide that you're going to apply whatever integration rule you know to this because it does not fit the rule. The rules are very important. The reason why I have you guys memorize it is because they're literally templates. The rules that you have memorized need to fit exactly on top of the thing that you want to apply the rule to. It is actually important that there's a 2 here as opposed to not being there. Right? That's what I want you guys to get through your head. Easy. Hard. In fact, this is impossible. Right? So you should know that. So now, because you know that because this here is squared, that's a problem, now you're going to think, how can I not make that a square? Is there any way to get rid of it? And yes, a substitution would be how you get rid of it. Right? So now you have the 2x dx. In fact, you know that that's 1/2 dt. Is going to give you the x dx. And so that causes you to split up as was suggested earlier. I can take one of the x's off of that guy. So this here becomes my 1/2 dt. This here is going to be my sine of t. What about this guy? It's just t. So this integral actually comes down to 1/2 the integral of t sine t dt. How do you do that integral?
By parts.
By parts. What are the parts?
Differentiate t, integrate sine.
Right, so you differentiate that. You integrate the integral of sine is?
Negative cosine. It's negative sine.
So it's going to be this times this plus, so that'll give you 1/2 times. So it's going to be minus t cosine t. This times this minus plus sine t. That times that's just going to be 0 plus your constant. And so we would get 1/2. Our t was x squared, so it's minus x squared cosine of x squared plus sine of x squared. You can bring the plus c outside. And of course, with the limits on the integral, you had to. So the rules are important. Is the first step. So. Step 1, you need to know the rules. You need to know them very well, because you should not make a move unless there's a specific rule that you know applies to this thing that I'm looking at that's going to bring me to the other step that I want to get to, right? And the rules must fit exactly on top of the thing. If a power is off, if you have absolute values, when you don't have absolute values, like it's very important that you know the rules extremely well. That's the first step. Know the rules. The second thing you want to know is to know the strategies. So, for example, you know the strategy of how to do a substitution. You know the strategy of how to do an integration by parts. And I'm going to tell you an overall strategy when you should choose which. But that is the second thing you need to know, right? You should know, based on a strategy, that before just like straight up jumping into tabular method, that means you're thinking integration by parts. But you know what? You should have thought of substitution before you thought of this, right? Substitution is step 3. Integration by parts is step 4 or higher, right? Why would you jump to step 4? You see that first thing. Is it a basic rule? No. Can I simplify it to a basic rule? No. Can a substitution work? Well, the sine of x squared is definitely a little bit complicated. I know how to do it with sine of x. So yeah, I'm going to do a substitution. Your mind goes there first. Then once you get through that, you get to a position, the substitution didn't really get me home here. I'm going to think of something else. Now you start thinking integration by parts, right? But at the end of the day, everything that's informing your decision is because of a rule that you know and a strategy for applying that rule. You don't just it seems like, it's a polynomial times a trig function, no, that's not how you think. You think based on a strategy. Is it a basic rule? Can I simplify it? Substitution. Then you think of something more sophisticated. Leading with the substitution was the better way here. There are ways to not do that, but it's probably outside of the scope of a Calc-2 student, average Calc-2 student. If I do it the other ways, like 98% of you would be confused as to what I'm talking about. Leading with the substitution is going to be a lot easier to process. So, yeah, let me go steal a eraser. Normally they lock them up. Okay, I'll be right back.
It's better to do it on your quiz than it's fast.
Yeah, I heard that too. So I was studying
Oh my god.
I tried to use the restoring life and stuff. It's still not working, so I don't know how to get the keys back. That's fucked up. You haven't we see like I just want to
Tweet them. You think it's funny? Like, it really works. Like, my girlfriend has no followers. She like had Sonic hair and came into the first program. Yeah, like sent her. Of course. It's public. It's basic public relations. Twitter is like a platform.
yeah, he's having like 4 meetings, so I like, you can't freaking
Alright, so we won't record. You don't need that PlayStation until the end of May.
it's sad, but like,
Sad but true. No, I only played the newest one. Like the old ones I checked out like that 90 times 99. All in that.
I only played 2 ones, the third and like the last 3 ones.
Yeah.
The new one's nice.
That quiz wasn't bad. It was fair. It was fair. Like if you know your shit.
It would have been more than you think.
Yeah.
There was one, like, you see the one example is G, but there was, for me, there was one with the stuff also was Sine.
Yeah, it was Sine.
I don't know how to do that.
I don't know how to do it. I just guessed that Secant I times Sine. Sine of negative 1. Maybe I'm wrong. I think so. Either that or most. I mean, most the answers are.
Yeah, I think you had it on the same.
I didn't buy it.
You said he was.
Yo, for one of these classes, it's the same problem, minus like 4 or 5 times. The same exact problem, 4 different quizzes. And people kept getting it wrong. So like it's definitely important to go back and like make sure you got 100 left. So it's like no problem without it's like everybody throws it on again. You'll be ready. No, dude.
Yeah.
No, I was
He wants that, so if you might ask him that.
Five squared.
So you guys finished the rest of them, right? classes were just as bad. All the supplies are the same. Literally had to run up to my office on the 6th floor to get this. So that's it's my fault. I forgot the rules at City College. You see that? You see how that catches you? Always bring all your supplies with you.
Always remember the steps you take.
Because I teach elsewhere and it doesn't happen. Like if I walk in a classroom, there's chalk, there's erasers. I never have to bring anything with me. Like here, I always have like extra chalk, extra erasers. Yeah, I forgot to. So supplies are scarce here. You kind of have to keep them close to the chest. Now, where are we? Okay. So, first step here. Yeah.
You can use sub t for radical x.
Right.
T squared equals x.
Because that is complicated. I don't know how to deal with a cosine of a radical x. I know how to deal with a cosine of x. So instead of the radical of some angle, I'd rather just have an angle. So for this reason, leading with a substitution makes sense. I first start out by doing that. Now, that of course means your dt. Now there are a couple ways you can do this. I can first square both sides, then differentiate. Or if you wanted to do that another way, well, you could have just differentiated right off the bat. You get 1/2 x to the minus 1/2 dx. Then you probably solve for the dx. That'll give you 2x to the 1/2 dt. But of course, you don't want x's mixed with t's, so you just replace that x to the 1/2 with the t because x to the 1/2 is t. Whichever way makes sense to you or brain more, do it that way, forget the other way. But that's how it would start. Now, once I make that substitution, this is going to get things to look closer to the rules that I have memorized. I'm going to now put this all in. So my dx gets replaced by 2 t dt. Now, and then I have my cosine of t times that. And then I have radical x in front, but radical x is t, so that's this guy. So I have this integral. How do we do that one?
Tabular.
Tabular, probably. Right, because if I did integration by parts, I'll have to do it twice. Integral of cosine, positive sine. So it's going to be 2 times. So it's this times that with a plus sign, t squared sine of t, minus this times that, plus this times that, minus the integral of that, which is the integral of 0. And my t is radical x. So that's just going to be x. That's going to be the answer. Okay, tangent inverse. How do you do with that? What?
Is it one of the simple rules?
Is it?
Or is it the derivative of inverse tangent?
Well, we know the derivative of inverse tangent. Yes, that's 1/1 plus x squared. What's the integral of inverse tangent?
You do integration by parts.
What are the parts?
U is equal to 1/10 of x and dv
Right, so it's very similar to the strategy that we saw with sine inverse. And again, I did go through the 3 steps in my head. Is it a basic rule? No. Can I simplify it to a basic rule? How are you going to simplify an arctangent? Can a substitution work? What would you substitute? But by parts seems to do fine. I know the derivative of this guy. I know the integral of this side. So now it's going to be, so this is my I is going to be equal to u times v minus the integral of the du. And how do I do this integral?
Substitution.
What do I substitute?
U is equal to 1 plus x
And so that's going to be your x dx. And so this I is going to be equal to x tan inverse x minus the integral of 1/2 1 over u du. Integral of 1 over u. Huh?
ln absolute value.
Absolute value of u. C. And yes, if you forgot the absolute value on the quiz, you do lose the point. Like I said, attention to detail, it is important. Every little scribble matters. So that's going to be x tan inverse of x minus 1/2 ln 1 plus x squared. And yes, technically you don't need the absolute values here because 1 plus x squared is always positive, but it's not wrong to leave it, so I'm going to leave it. It might be wrong for you to forget it. Yeah.
In that problem at the bottom, why is it minus sine? Yeah, that one. Why is it minus sine t instead of minus 2 sine t? You not have to go.
Yes, that should be it. This right here, you mean?
Yeah.
Yes, that should be it. Good thing we caught it because I was about to do this. And that was the last one. So, we are going to move on, but hopefully all these little lessons that we're picking up by going through these examples, I hope you're taking away from it the things you should be taking away from it, like how to approach a problem. Like a lot of students, they're reading over their notes, they focus on the examples, and they said, and they just decide, hey, let's try this and see if it works out. Or, last time we had a problem like this, Jhevon tried something like this, so let me try something like that. Right? They don't really know why they're doing what they're doing, and how you want to know why you're doing what you're doing is first, know the rules, second, know the strategies. Then the path becomes clear. So whenever you're reading over your notes and you're studying for a test, those are the two things you need to learn first. Don't just immediately look at the examples. Look at what were the rules that we covered in this section, what are the strategies we covered in this section, then you practice examples, right? Because the examples are just me showing you how the rules apply, right? So if you're going to get lost if you kind of focus on the examples and all the math, you get lost in it. You do need some sort of focus here. Why am I doing what am I doing? Why was this the best path and not that? You need to know these things. It'll save you time, and sometimes it helps you get something correct, what you would have gotten incorrect in the first place. So we're going to move on to the next section, 8.3. And as you would have guessed from the bonus, this is going to be about trig integrals. Learn how to integrate stuff with trig functions. Everyone loves trig functions. Trigonometry is our favorite thing. Of course, let's learn how to integrate them. So, what are we talking about here? The main idea, goal, is to be able to use trig identities to help us solve integrals. What's the best way to actually go about doing that? Is going to be what we're going to look at in this section. And I'm going to cover a few important cases with you. But before, let's just jump start into an example. How do you do that integral? Yeah.
I say convert that into sine squared x over cosine squared x, and then change sine squared x into 1 minus cosine squared x. And I believe you can take those
Yeah.
You divide the numerator by the denominator, which will get you to secant squared x minus 1.
Right, which by the way, is an identity. Right? Tangent squared is equal to secant squared minus 1. Right? So you probably didn't have to go through all this to get there. Identity. That's an identity. Why is that identity useful?
Because the integral of secant squared is 10.
Right, you do know the integral of secant squared. Do you know the integral of 1? Why is the integral of 1x?
differentiate x to the first power. You would have 1 times x is 0.
Is that x?
It's u.
Huh? And do we get y?
It's with respect to
U is the independent variable. X is the independent variable, right? So again, notation matters, right? So the integral of 1, say, think of the integral of 1 as x. Maybe you can get away with doing that, but you really want to think of the integral of 1 dx is x plus c, right? Your integral matters who your variable is, right? So if you have a du's, you're thinking in terms of u's. If you have dx, you're thinking in terms of x's. If you have dt, you're thinking in terms of t's. If you have dp, you're thinking in terms of p's. So I just want to make sure that we all understand that. My other class actually had trouble with that. We did a u substitution, and we had like 1 du, and some people shouted out x. I'm like, no, it's not x. Pay attention, the details matter. But yes, it's x because of the dx. Yeah, but that would be the integral. Right? How do we figure that out? With a trig identity. Right? So we want to learn to do more things like that. How can I use these trig identities to help me figure out an integral that might be kind of difficult to deal with in the beginning? So some other useful integrals We all know the integral of sines and cosines, but do we know the integral of, say, secants and tangents? How do we do this integral? And?
Subcosine. You should get the negative integral of 1 over u.
So this becomes minus 1 over u du. Integral of that?
Negative absolute value.
So that leads us to minus ln of cosine plus c. So, by the way, that can be a rule now that you can remember. Some people don't like that rule for aesthetic reasons. Usually, another way you can look at this is remember laws of logarithms. If you have a multiple of a logarithm, you can bring that up to a power. And of course, absolute value of x to a negative 1 is the same as x to the negative 1 raised to the absolute value. So this is like 1 over cosine, which gives you sine, which gives you secant. So, probably memorize this. But this was one of the bonus problems. What is this? This is a rule now. So what you want to do is you want to remember that this is a rule. Integral of tangent x dx equals that. And so that's a rule now. That's something we know. Another thing that we're going to want to know how to do is integrating the secant function. So I don't know how to integrate secant. Ideas? One over cosine, then what would you do with that? Okay, and your du would be?
Can you integrate cosine x to the negative first power?
I know,
Sorry,
can you?
sorry, quantity to the negative first.
I don't know, can you? Yeah?
Will rewriting that be square root of 1 minus 10x?
Sure, is that helpful? It would be the square root of 1 plus tangent squared of x. Right, 1 plus tangent squared equals secant squared. So if you want to solve that for secant squared, you can write as the radical of 1 plus tangent squared, which doesn't seem any nicer. So this one is kind of strange. Yeah?
1 over cosine, and then you do 1 is equal to sine squared plus cosine squared.
And how does that help?
You want to separate them and get sine squared over cosine plus.
Okay.
And then you
Now, of course, the cosine square of a cosine is going to be easy to deal with. How would you deal with sine squared over cosine?
One of them would become tan x, and the other would be
secant. Could be tan secant.
Okay, and how would you do that?
The integral that is.
Right, you'll kind of end up in a loop here. Let me tell you how the traditional way to do this. It's going to be weird. I'm just going to tell you off the bat. Yeah.
Isn't it by parts?
No.
No?
Yeah. So I'm going to tell you the traditional way to do this. It's one of those things where if you've never seen it before, you're probably never going to come up with it. Honestly, I don't tell you. The first person to come up with this, I can't tell you what possessed them to come up with this. But they came up with this, right? I'm actually going to show you another way to do this that's a little bit more constructive. But this, it comes out of nowhere. Okay, so the person saw this and they went like, okay, I'm going to multiply and divide by something convenient. What is that thing? That. Now, before you say, well, how does that make things nicer? That looks more complicated. Hold on a second. And some of you are like, Jhevon, I feel like we're making matters worse here. Like I don't see how this is gonna work out for us. Now, do you see anything? Huh?
Separated into two fractions.
And then you go back to reach
Yeah.
Yeah. Substitute what?
Oh, tangent.
If our u is equal to secant x plus tangent x, what would our du be? Secant x tangent x is the derivative of secant. Derivative of tangent. Like, oh, he's like, oh, like out of nowhere. It's like, he like hit a 3-pointer from half court. Like, where did that come from? Oh, yeah. That's the numerator. So this guy actually becomes 1 over u du with this substitution. So this guy becomes ln of the absolute value of u plus c, which is ln of the absolute value of secant x plus tangent x plus c. Now, I want this to be a rule, so I'm going to write it out in its entirety. So this is just something else we know now, right? It was also on the bonus problem on the quiz. This is the integral of secant. So that's a rule. You know that. So I'm going to teach you a technique that has a little bit more of a constructive solution to it, but that comes later. I'll teach you that after partial fractions. For now, that is the traditional way that this guy is integrated. By the way, to integrate cosecant is actually a very similar strategy, actually. You just multiply by cosecant plus cotangent over itself. But that's the integral of secant. Now, something worth mentioning at this point. So, sines, cosines, you know how to do with those, and now you know how to integrate secant and tangent. At this point, I'm just going to tell you unless incidental, meaning like on the homework or some odd problem where it's going to be extremely nice, we will not focus or pay any mind to at all on cosecant and cotangents in this section. Right, so the integral of cosecant, integral of cotangent, you don't have to memorize the formulas for that. One reason why is because secants and tangents will behave a lot like cosecants and cotangents. So if I teach you all the strategies for secants and tangents, you'll automatically know the strategies for cosecants and cotangents. So it's just like me asking you to memorize a bunch of extra rules without you really learning anything for it. So we're not going to do that. And it's not a very common thing to ask. So even if we were in a section doing a uniform final, you seeing having to deal with these guys in integrals on a uniform final, it's not going to happen, right? You'll see sines, cosines, secants, and tangents. So in terms of integration and differentiation, you don't really have to worry about these guys too much. Worry about the secants and tangents. So if you're thinking about what rules I have to memorize, you can pretty much ignore anything with a cosecant and cotangent. That being said, let's move on. So I'm going to teach you how to deal with, if you have the product of sines and cosines, and if you have a product of secants and tangents. Now, what if you have a mixture of sines and secants or cotangents? What if these guys start mingling together? Well, the technique that I'm going to teach you to do that will handle that. In this section, we're going to focus on these guys specifically. If you have a product of sines and cosines, or you have a product of secants and tangents, perhaps raised to some weird powers, or just, I guess the third case, just products of functions of sines and cosines. So these are the main cases. Most of our attention is going to be focused on these two because with those two and what you know about substitution and previous integration techniques, you'll be able to deal with these afterwards, right? You'll just know how to manipulate them to get into a situation that you know how to deal with. So we're not going to really focus on 3 and 4, but 1 and 2. I want to know how to deal with these cases. So that's going to be the focus for this section. Let's deal with the sines and cosines first. One thing I want you to know is that this case has subcases. So 1, 2, 3, 4. The strategy will vary based on what the powers are. So if you have m is odd, n is even. If you have n is even, n is odd. Or if you have them both odd, or both even. So even, 0, plus or minus 2, plus or minus 4, plus or minus 6, plus or minus 8. Odd, plus or minus 1, plus or minus 3, plus or minus 5, etc. So we're going to break them down. Now, cases 1 and 2, they're very similar. Like whatever you kind of do in case 1, you'll kind of just flip it and do it in case 2. So whatever the role that sine played here, the cosine is going to play here. So those guys are going to be very similar. So let's just deal with, let's say, case 1. So let's suppose you have an odd power of sine and an even power of cosine. What are you going to do? So here are the steps. So this is what you should be paying attention to, the strategy. The first thing you're going to do is you're going to save a factor of sine. Okay. I'll talk about saving just means like literally factor it off and separate it and just kind of have it sit there. 2, we're going to change all other sines to cosines. How are you going to change them? Using the identity, cosine squared plus sine squared equals 1. So you can rewrite all other sines using sine squared equals 1 minus cosine squared. 3, you're going to do a substitution. Equals cosine. Your du is going to be that sine that you had saved, so you're going to be able to take that, and because you change all other sines to cosines, you're just going to now have a function of u. Integrate. Do your thing at this point. At this point, you should be in a familiar situation. It's not going to be too hard to deal with. So. Example. Next one. B. I'm just doing. Probably should have done that first. Or let's look at those. That to be a squared. Because that's not even. That's cosine squared. Alright, so the sine is cubed and the cosine is squared. So the sine has an odd power, the cosine has an even power. Whenever you see that, what do? You save a factor of the sine. So I'm going to factor off a sine, I'm going to tack it on to the end over here. Just leave it there. Step 2. And change all the remaining sines to cosines. How are you going to do that? With the trig identity. you're going to do a substitution. U equals cosine. Your du is going to be, of course, minus sine of x dx. And so now, this will become that, which of course is not a bad integral to deal with. So, this is going to be the integral of u to the 4th minus u squared du. And from there, it's just the power of 1 to the 55 minus q over 3 plus c.
Wouldn't it be u squared minus
Come again?
Wouldn't it be u squared minus u to the 4th?
Ah, but there's a minus up there.
Oh, sorry.
Yeah. So I brought that minus in when I was multiplying up. And that's that. Not so bad. Well, no individual technique is usually that bad. It's just that when you have a mixture of them, how to know what to pick, what to do. But yeah, that if you have sines and cosines, you have an odd power of sine, an even power of cosine, then you do this. You save a factor of sine, change all the other signs, do a substitution.
Sorry, how did that minus sign get there?
Come again?
That minus sign that he just asked you about, how did it get there?
From the substitution.
Oh, okay, sorry.
So the derivative of cosine is minus sine. Don't say sorry. Don't apologize for asking a question. It's literally why I'm here, to answer the questions. Now, you look at this, and you might wonder, is this a product of sines and cosines that's in this form? And yes, because notice here that the power of cosine is what? 0. Right? But cosine to the 0 is just 1, so you don't see it. So whenever you don't see something, and this is something you're going to want to think about a lot, like all the time. Whenever you don't see something, you can always get something in there that might not be in there by thinking of it, oh, it's just to the power of 0. Right? Like another way to think about why the integral of 1 dx is x is to actually think of that 1 as an x to the 0 and then apply the power, right? So you kind of have that, the power to do this manipulation, right? Add 1 to the power divided by the numerator. And of course, if it was a du, you think of it as u to the 0 because u is the variable that you're working with. So this is an even power because 0 is an even number. So you see that? We're going to do the same strategy. I'm going to save a factor of the sine. Change all of their signs to cosines. Then do a substitution for the cosine. D is going to be the minus sine. And so this is just the integral of, well, it's 1 minus 1 minus u squared. Questions on this one? Case 2, similar to case 1. Just switch the roles of sine and cosine. that should actually explain everything, so let's just knock out an example. So here I want the sine to be even and the cosine to be odd. Let's say I have sine squared times cosine to the fifth. What do we want to do here? This is going to be 1 minus sine
Squared x squared.
Quantity.
Right. It's not 1 minus sine to the fourth x. That's distributing powers across sums back there. If you thought about that, that's where the mistake is. It's a blasphemy. So you just think of cosine to the fourth as cosine squared squared, and you can change the cosine squared. So now, your u goes to the sine of x, and your du is going to be the cosine of x. And so this just becomes u squared times 1 minus u squared squared du. How do I do this one? What happens here? Huh? What is this? Expand to. So this is going to be sine cubed over 3 minus 2 sine to the fifth over 5 plus sine to the seventh over 7 plus c. Right, so similar idea. So if one is odd, one is even, you save one of the odd ones, change the trig function to the other one using the Pythagorean identity, and then it brings you into an easy u sub case. What if they're both odd? It's 3. So if both are odd, step 1, you save a factor of the smaller power of the trig function with the smaller power. Change everyone to the other trig function. Using, of course, cosine squared plus sine squared. And again, substitution. Shouldn't really use substitution. Picking up bad habits from my students. And of course, multiply. Now, substitution as appropriate depends on who you saved, who you changed. Let's do an example. let's say you had sine to the fifth, cosine cubed. Want to do that one? So you want to do, what do you want to do here?
Save cosine.
Say cosine. So they're both odd. So you notice that they're both odd. You want to save the smaller power. So you have sine to the fifth, cosine squared, cosine. Now I'm going to want to change this to the other trig function. So this is sine to the fifth, 1 minus sine squared. Now I'm going to do the appropriate substitution. Of course, I want my du to be the cosine, so my u is going to be the sine. And you plug that in. So that's going to be u to the fifth times 1 minus u squared du. This is going to be u to the fifth minus u to the seventh du. And that's going to be u to the 6 over 6 minus u to the 8th over 8 plus c. U sine. Now, technically, I just want to mention, technically, either choice you made here would have worked out in the end. You could have saved a factor of the sine, but I just want to show you what's going to happen. So, suppose you had sine to the fifth x, cosine cubed x dx, and you decided to save one of the sines. So now you're going to have to change this sine to cosine, which is 1 minus cosine squared x, all squared, cosine cubed x, sine dx. So you're at u equals cosine, du equals minus sine. And so you would end up with minus 1 minus u squared squared u cubed u, which is doable, but you'll actually notice that it is harder than the previous way. Like here I'd have to expand more. And so that's why I say the smaller power. Not because you can't actually do it the other way, but by doing the smaller power, you have less algebra to worry about. Right? Because once you change the guy with the bigger power, you now have more multiplying outs to happen. Right? So if this was like to the 7th, then it would have been this to the cube, and now you have to cube it out, right? As opposed to this way wouldn't actually matter, wouldn't be much different. That's just now 7. Right? So saving the smaller power actually makes less work. So that's why the steps is to save the smaller power. But you could have saved the larger power. It would have worked out. It will take more algebra, but it can also work out. What if they're both even? So, right when they're both even, what you're going to do is you're going to use a different identity. You're not going to use the cosine squared plus sine squared equals 1. You're going to use these double angle formulas slash half angle formulas. They're the same formula. Okay, I never know which one to call that equation. Let's call it double angle formula. Right, which we all remember from Calc 1 and pre-calc and algebra. Like there's so many reasons why we should remember this. But you should know how to write, well, these aren't the important ones, but for this application, but in general, you should know, what is sine of 2x?
2 sine x cosine.
So you should know that that's it. What is cosine of 2x? No. You guys are taking too long. You need to remember this is cosine squared minus sine squared. Now, if you use the Pythagorean identity to change the cosine squared, say change the cosine squared to 1 minus sine squared, it's also 1 minus 2 sine squared. And if you use the Pythagorean identity to change the sine squared to 1 minus cosine squared, it would become 2 cosine squared minus 1. And these are the two important versions that connect to this, is what we're going to want to know. Because if you use these two equations, this means you can actually rewrite, say, a sine squared. Right? I can just solve this for sine squared. You'll end up with 1 minus cosine 2x all over 2. And you can actually rewrite cosine squared using this equation. 1 plus cosine 2x all over 2. And these are the guys, the versions you're going to want to remember for this application. But really, you should remember all of these. Now, how is that going to help us? Because that allows us to look at even powers of sine and cosine, namely the power 2. Now, of course, if we have the power 4, we can just think of that squaring both sides of that equation. Or the power 6, we can think of cubing both sides of that equation, etc. So we can actually generate all the even powers from these two equations. So maybe I'll just run my sine examples. Let's just straight up integrate sine squared. Let's back to the reader. What about sine squared x times cosine squared x? And what about something like sine to the fourth x times cosine squared x? Now, of course, here you can think of both as being even powered. Cosine is to the 0th power here, sine is to the 0th power here. But here they're both like visible. Now, once you have even powers, and they're both even, so you can't like save a factor and get something nice. Right? You save a factor of your cosine, now you have 1 cosine. If you change that to sines, you're going to introduce a radical into this equation, which is not going to make it any nicer. So, whenever you see like all powers are evens for the sine and cosine, there's no odd power to kind of save a factor with, you apply those two formulas, whichever one is appropriate. So, for example, you want to integrate sine squared. What do you want to do here? Huh? Literally just going to change it according to that. And at that point, you can actually start doing integration. Integral of 1, x, because it's dx. Integral of cosine of 2x.
1. Negative 1.
Now, technically, that's a u substitution. But technically, it's also the kind of u substitution you should be able to do in your head, because your u, if you say u equals 2x, your d is just going to be a constant. And that's the only situation in which you can just divide by the thing, right? If this was an x squared, the derivative is 2x, you can't just divide out by the 2x, it doesn't work. If it's a constant, you can do that. Once your substitution is a constant, then your integral is just going to be 1 over the constant times the integral of the term, right? So things like that, I don't expect you have to do a u substitution for. So if you have integral of sine 5x, well, it's going to be minus 1/5 cosine 5x. I don't expect you to have to do a u substitution for that. So yeah, just divide by the 2 and take the integral. But technically speaking, technically substitution. So it's not like you can always just divide by the derivative and hey, that's my integral. It doesn't work in general. But yeah, that's your answer. That's how you integrate a sine squared. And obviously the cosine squared is going to be very similar. It's literally just a sign change. How would you do that? Ideas? Yeah.
Sub sine squared x for 1 minus cosine 2x over 2. And then you have all equal cosines. Yeah, you can just distribute integrate, can't you?
If we integrated the... How would you integrate that?
If you distribute,
So you get cosine squared minus cosine squared times cosine 2x.
yeah.
How would you integrate that? Look at the cosine squared times cosine 2x part. How would you integrate that?
Possible.
Huh?
Possible.
It's possible. You want to apply the identity to this as well. Now there's another way to do it, but I'll follow it. There's an easier way to do this particular example, but let's run with this one. It's not wrong. What are you going to get here? Well, the 2's you can factor out as a quarter. So you're going to have 1 minus cosine 2x times 1 plus cosine 2x. What is that?
1 plus cosine squared of 2x.
1 minus cosine squared 2x. That is the difference of squares. 1 minus cosine squared 2x. What is that? That's just sine squared, right? So this is actually 1/4 times the integral of sine squared 2x, which that was the better way to actually see that right away. How would you see that right away? Well, this is just sine squared, cosine x all squared. And you know sine x cosine x is actually 1/2 sine of 2x all squared. So that's actually 1/4 sine squared 2x right away. But of course, if you do this, eventually you'll get there. If you're very quick with your trig identities, you're not going to lose a lot of time. I'm not going to not recommend that. It's fine. But essentially now how would you deal with that part? How do you integrate sine squared 2x? Use that in it again, what do you get? So it's 1/2, right? Times the 1/4, so that's 1/8. of 1 minus cosine 4x, right? Double the angle, so it's called the double angle form. So now, so everything else stays the same except you double the angle, right? So sine squared 2x is 1/2 1 minus cosine 4x. Sine squared of 6x is 1/2 1 minus cosine of 12x, etc. And you just double the angle. And that you should be able to integrate. Okay, integral of 1 is x, integral of this is 1/4. Let's see. That's that. That was D. What do you want to do here? I'll let you guys do it. We'll pick up on Wednesday. So next thing I'm going to move on to after this exam is going to be the product of secants and tangents. So maybe you want to try to read ahead on that. Next. And I'm going to take this with me. I don't like always have to carry it.